This video note is working through homework problem 1681L in Greenberg, and the idea is that we're going to both, for a given region, this is a tetrahedron, we're going to compute the volume integral of the divergence and the surface flux of the vector field. So first let's talk about the region. This is a tetrahedron, so we're going to be, it's a right tetrahedron at the corner. So this is my z-axis, x and y. So here's x, y, z. And so we're told that 3 of the 4 faces of the tetrahedron are just the xy, the y, z, and the zx planes. And there's an oblique plane that's cutting through that corner, and that oblique plane has the functional form 2x plus y plus 2z minus 2 equals 0. Clearly that's an equation for a plane, and I can draw that plane just by thinking about the intercepts. So the x-intercept when y and z are both 0 is just 1. So x equals 1 is one intercept of that plane with the x-axis. When x and z are both 0, y has to be equal to 2. And then when x and y are both equal to 0, z has to be equal to 1. So this is my plane slicing through, and I will just draw the intercept of that plane with the xz plane, the intercept of that oblique plane with the xy plane, and the intercept of that plane with the yz plane. Okay, so I have a little tetrahedron. It's like a tent in the corner of the room. And the vector field, whose divergence we want to integrate over the volume, the vector field v, is z squared k hat. Okay, so it points straight in the vertical direction, and we can immediately take the divergence of v. So there's no I hat or j hat component, and so we need to take the partial derivative with respect to z of the k hat component, which is just 2z. Okay, so now to set up the volume integral. So part 1, we need to do volume integral of the divergence. So integrating over that volume. And as usual, let's set that up as an iterated integral. And so we have to think about how we're going to write the limits. And so I would do an integral over z for every value of x and y. So here's some point on the surface. Okay, so first I'm going to integrate over z for every x and y. Then I will integrate those integrals over y, and then finally over x. So x will be the outermost and z will be the innermost. So I need my limits z max as a function of x and y. And if I look at the equation for the plane, z max. So I'm just solving the equation for the oblique plane in terms of z as a function of x and y. And so z max will be 2 minus 2x minus y over 2. Okay, and then I have to look in the xy plane to see what my limits on y will be as a function of x. So if I project into the xy plane, this is x and this is y, x equals 1, y equals 2. So this is the region of integration in the xy plane, and so y max, I should also say z min, is equal to 0, because if I look on the z-axis, the lower limit is always z equals 0, this plane on the bottom. That's my lower limit on z. And now if I look at my limit on y as a function of x, at z equals 0, I can look at my expression for the plane. When z equals 0, it tells me that 2x plus y has to add up to 2, or otherwise y max is equal to 2 minus 2x. Okay, and then of course x max is just 1. So those are my limits of integration, and when I set up my iterated integral, I know that the divergence is 2z. I already computed that, so the object that I'm computing, let's call this the integral capital I. So the integral, I need to integrate, the outer integral is over x, then my integral over y runs from 0 to 2 minus 2x, and then my integral over z runs from 0 all the way up to 2 minus 2x minus y over 2, and the thing that I'm integrating is 2z dz dy. dx. Okay, and so this is really, at this point, it just becomes undergraduate, even high school calculus. And I don't like doing high school calculus, so I'm going to let Mathematica do it for me. I will show you guys how to do that. So let's go to alpha.wolfram. And so I can do the inner integral, and I'm going to integrate 2 times z, and I'm integrating from z equals 0 up to z equals 2 minus 2x minus y, all divided by 2. That's my upper limit of integration. Oh, I'm sorry, I'm integrating with respect to z. Okay, there's my answer. It's 1/4 2x plus y minus 2 squared. That's what I get when I integrate over z from 0 to z max for given x and y. And so really I'm interested in the integral. I have to integrate that integral over y. And y runs from 0, and y max is 2 minus 2x. Let me make sure I have a multiplication in there. Okay. So now I'm integrating over z for every y and x, and I'm integrating that over y for every x, and I still need to integrate this quantity over y to find a final answer. So I need to integrate that. Integrating it over x, and x goes from 0 to 1. And so the final answer is 1/6. So this is equal to okay, so that was part 1, where we're integrating the divergence of that vector field over the volume of interest. Now what we need to do, so part 2, is we need to integrate the flux over the surface. So I'm integrating over the boundary of that region, and the thing that I'm integrating is the dot product with my unit area, my unit outward area element. Okay, so as before, the example that I did in class, I'm going to break my polyhedron up into the faces, and so this is a tetrahedron. There are 4 faces. There's the xy plane, the yz plane, the zx plane, and then the oblique plane. Okay, so let's look at those faces. Let's give them names. So face 1 is the xy plane. Face 2 is the yz plane. Face 3 is the zx plane. And then face 4 is the oblique one, which was 2x plus y plus 2z minus 2 equals 0. Okay, let's think about the flux on each of those faces. Immediately, since our vector field, remember v, let's look at what it is. It points in the z direction. So I'll just copy that. V is equal to z squared k hat. we immediately know that the YZ plane and ZX plane have no flux. So YZ plane, so face 2, the normal vector is I hat. Face 3, the normal vector is j hat. So there's no flux from phase 2 and phase 3 because v is proportional. It points in the k hat direction. Okay, so there's absolutely no flux. The vector field points in the plane of phase 2 and phase 3. So phase 1, the normal vector, the outward normal vector is minus k hat. Okay, so we've got a chance, but for phase 1, z is equal to 0. And if I look at my expression for the vector field, it's equal to 0. The vector field is just turned off. I don't care where it's pointing. Z is equal to 0, so it's 0 everywhere there. So v is equal to 0, so there's no flux on phase 1 either. No flux. So the only flux is coming from phase 3, from the oblique face, from phase 4. Flux is not equal to 0, and if we believe the divergence theorem, we should come up with an answer of 1/6. So let's use our favorite naive parameterization, and so let's write z as a function of x and y, and let's integrate over x and y. So naive parameterization, so let's write x is just equal to x, y just equal to y, and then I have to write z as a function of x and y, and that's just the equation for the plane. So z is going to be equal to 2 minus 2x minus y over 2. So that's my parameterized surface. And I can construct my tangent vectors for the surface. So that's just going to be I hat. Then I have to take the derivative of z with respect to x, and that gives me a -1. So it's going to be negative k hat. And then my other tangent vector on that surface is going to be the tangent vector in the y direction, which is always j hat. And then I have to take the derivative of z with respect to y, and there I get a half. So it's -1/2 k hat. And then to get my normal vector, again, this is not a unit normal. This is my unnormalized normal vector on the surface. I have to take the cross product between the my two parameterized tangent vectors. And so that normal vector, when I do the algebra, I'll let you guys do the algebra. It comes out to be k hat plus I hat plus 1/2 j hat. Again, I'm just taking the cross product of those two things. I'm suppressing that here. And so at this point, we always have to worry, is it outward? And in this case, yes. So we just have to look, and we see that this thing is pointing out of our tent, not into our tent. So we got lucky, and we chose the right parameterization that would give us an outward normal vector. Otherwise, we would have to put a minus sign on it so that it was pointing out. But this one is naturally pointing out. Okay, so we're good. That means the integral that I have to do, so the total flux through that surface, so our area element, dA vector, which is also known as n hat dA, is just n dx dy, where this is n, that's the outward normal vector, not unit normal, but it's the one that has the right measure when we multiply it by dx and dy. Okay, and so that's equal to our area element, dA, is equal to k hat plus I hat plus 1/2 j hat. I've just copied that down, and times dx dy. And so to find the flux, I need to integrate over the surface. I need to think about my limits on x and y. We'll talk about that in a moment, but the thing that I'm integrating is my field, which is z squared k hat, and I have to take my field, my vector field, and dot it with the area element, which is k hat plus I hat plus 1/2 j hat, and dx dy. Again, I'm being sloppy. I haven't thought about the limits yet. I'll think about the limits in a moment. So clearly, since I've got a k hat here, these two pieces really go away and don't contribute. And so the answer is that the flux is going to be the integral of z squared times 1, so k hat dot k hat is 1, and k hat dot I hat is 0, k hat dot j hat is 0, so I only have one of those three terms contributing, and I'm still integrating over x and y. Now I'm going to think more seriously about the limits. I will do an integral. So first of all, I know z as a function of x and y looks like this. So let me express z in terms of x and y. So z is 2 minus 2x minus y over 2. Okay, and that thing has to be squared. And then if I think about my region of integration again, so if this is x and this is y, the intercept over here is 1, 2. I'm integrating over this region. And I will do an integral over y for every value of x. And so from before, when we were doing our volume integral, we realized that y ran from 0 to 2 minus 2x. So that's my integral. I'm integrating with respect to y, and my limit depends on x, and then I finally integrate with respect to x, and x goes from 0 to 1. Okay, and if you actually look at this, the integrand right here is precisely what we got from the volume integral when we integrated over z. So we know we can go back into Mathematica, but we know that this will give us 1/6, just like before, because our, the integral, the integrand here, when I'm integrating over y and x, is precisely the same as before when we just had the integrand, when we did the first integral over z, and we were left with an integral over y and x. The integrand was in fact equal to 2 minus 2x minus y over 2 squared. So we know that has to equal 1/6. So good. The divergence theorem works out as we knew that it must.